video, we're going to start talking about nuclear radiation. But before we do that, let's just revisit our general model of an atom. An atom is composed of three main particles, and those particles are our negatively charged electrons that are circling on the outside of the nucleus. So these are the guys that are involved in chemical bonding. Then we also have our neutrons, our neutrally charged particles, and our protons, our positively charged particles that make up the nucleus or the center part of our atom. In nuclear chemistry, we're just focused on the changes that are occurring within that nucleus and kind of forgetting about these electrons on the outside. So just looking at those neutrons and those protons. Okay, so you may have heard of radioactivity before, but this is describing a nucleus of an atom that is unstable. So when a nucleus of an atom is unstable, it's going to release or emit or give off certain kinds of radiation. So what this radiation is it could be different kinds of rays and particles that will be emitted by this radioactive or this unstable nucleus of an atom. So in this picture here, it's just showing a few different examples of something called an alpha particle that can be emitted, something called a beta particle, and something called a gamma ray. So there's a few different more that we'll talk about. But the purpose of this unstable radioactive nucleus in releasing these different kinds of emissions is so that it eventually can become more stable. Okay, so why are some atoms unstable and why are others stable? Okay, so this all depends on the ratio of the neutrons to protons in the nucleus of an atom. So the higher this neutron-proton ratio, the more unstable the nucleus will be. So if we look at this chart over here, this just shows a diagram of what those neutron to proton ratios could be and whether or not that atom is radioactive or non-radioactive. So the blue in this thin line is showing the non-radioactive isotopes of atoms. So that means that they do have a stable neutron-proton ratio, whereas in green show the radioactive isotopes that have a higher neutron to proton ratio, making them more unstable. So the ones in green will spontaneously emit different kinds of radiation in order to try to be stable again. So large atoms are typically radioactive or naturally radioactive if they have an atomic number that's greater than 83. So atomic number 83, meaning 83 protons, is bismuth. So really large atoms are going to have a really high neutron-proton ratio, which causes them to be naturally radioactive. Smaller atoms can be radioactive as well, and this usually occurs when an atom's mass is not its typical mass. So a good example is the isotopes of carbon. So a typical isotope of carbon would be carbon-12. So mass number of 12 means that carbon-12 has 6 protons, because carbon will always have 6 protons. That's its atomic number. And then it will also have 6 neutrons. So it has a 1-to-1 ratio, so very low neutron-proton ratio. So carbon-12 is very stable. However, other isotopes of carbon exist, like carbon-13 and carbon-14. And this is when that neutron-proton ratio is going to get a little bit higher. So for carbon-13, we have 7 neutrons instead of 6. And then in carbon-14, we have 8 neutrons instead of 6. So both of these isotopes, or we can call them now radioisotopes, radioactive isotopes, are unstable. So these will spontaneously emit different kinds of radiation in order to try to become more stable. Okay, so types of radiation. So you have a table called Table O that shows the different kinds of particles and rays that you can possibly be asked about. However, the three main ones are alpha particles, beta particles, and gamma radiation. So this picture over here is just showing that if all of these different particles and rays were sent through an electrically charged plate, the top plate is positively charged and the bottom plate is negatively charged. This says that our beta rays would curve upwards towards the positively charged plate. The gamma rays would go straight through, being unaffected by those two charged plates. And the alpha particles will bend downwards, closer towards that negatively charged plate. Okay, and this is all due to the fact that some of these particles can have charge and sometimes they don't have charge. Okay, so this is just a quick little diagram, but if we look at these different notations, we can see that an alpha particle is essentially a helium atom. So the number on the top represents the mass of the particle, and the number on the bottom represents the charge. So helium has a charge of 2. If there's no positive or negative sign in front of it, it means we assume that it's just positive. An alpha particle is positively charged, so when it's sent through this plate, because negatives and positives attract, it will bend downwards as a result. A beta particle is just an electron. So an electron will have a mass of 0 and a charge of -1. So when that's sent through these electrically charged plates, those beta particles or those electrons will bend upwards, closer towards that positively charged plate because our positive and our negative attract towards one another. And then lastly, for our gamma radiation is photons. So photons is just light or rays of light. And gamma rays have this gamma symbol, and it has a mass of 0 and also a charge of 0. So it's neutrally charged. So when a neutrally charged particle gets sent through electrically charged plates, it's unaffected by the positive and the negative charge of this plate. So it just sends straight through. So you can see that there's some others as well. We have neutrons, which are also neutrally charged. We have protons, which are like our hydrogen. Okay, so it's going to have a +1 charge. And then we also have something called a positron, which is a positively charged electron. So this is just showing what those numbers mean and what those notations mean again. And these will become really important when we start trying to draw and read our nuclear reaction equations. So the number on the top, just remember, is the mass, and then the number on the bottom represents that charge. Okay, unless it's 0, if there's no positive or negative in front of it, it just means that it's positive. Okay, so we also have to talk about something called penetrating power and ionizing ability, okay, in terms of these different kinds of emissions. So penetrating power is basically how well is a particle able to penetrate different kinds of surfaces. So in this diagram here, we can see that we have an alpha particle, a beta particle, a gamma particle, and also neutron. And all of those are sent through like these different levels of materials. So the first material is paper, can also be thought of as skin. So an alpha particle, due to its mass and its high charge, okay, when you send an alpha particle through or try to get it through a paper or even skin, it doesn't have the power enough to penetrate or break through. Okay, so that's why we say that an alpha particle will have the least penetrating power of the 3 main types of radiation. The particle that will have the most penetrating power is going to be more commonly your gamma particles or your gamma radiation that you see on the questions, but your neutrons as well. So take the gamma ray, for example. A gamma ray has no charge at all. So when that is sent through these different materials, it'll penetrate through the paper, it'll penetrate through the aluminum, and then it'll stop at something like a heavy metal like lead. You can even think about this example of a lead apron that you have to wear during an x-ray. So if you ever got an x-ray before, like at the dentist, or if you ever broke a bone, they will always use this lead apron to place over your body in a different area that is not actually being x-rayed. So x-rays are not the same thing as gamma rays, but they are very similar, okay, in terms of this penetrating power. So x-rays have the power to pass through things like skin and aluminum, but not lead. Okay, so in order to minimize the amount of radiation that enters our body during an x-ray, we will use these lead aprons to block those x-rays from getting to other parts of your body where it's not necessary. Okay, however, those x-rays can pass through your skin. Okay, therefore they pass through, they light up, and you can take an image of it and see what's going on in your mouth or whatever's injured in your body. Now for ionizing ability, this is the ability of a nuclear particle to force an element to become an ion. So it's all dependent on the charge. So some particle or certain kind of ray that has a larger charge will have a greater ionizing ability. So out of all of our particles, in this diagram, and even if you looked at table O, the one with the largest charge is our alpha particle, has a charge of 2 or +2. So that means that alpha particles will have the most ionizing ability. And then the particles that will have the least or the lowest amount of ionizing ability would be those with smaller charge, or think no charge at all. So like your gamma rays, no charge, and even your neutrons have no charge. Okay, so those are going to have the least ionizing ability. Notice how for the alpha particles and for the gamma particles, both of these terms are flipped. So that can be a helpful tool to remember. Alpha particles, least penetrating, most ionizing. Gamma particles, most penetrating, least ionizing.